Hello, physics students. Welcome to week 2. Probably now you should have finished your FRQs and you have some of your work in front of you and are watching this video to get some hints on how to correct your work so that you can get the maximum points possible. As a reminder, this week there are 4 FRQs. The expectation is that you do at least 3 of them. If you're aiming to get a 5, you should be doing all of them for practice. As a reminder, again, you need 45 to 50-ish points, depending on how the points are distributed each year, to have that passing score. So don't get frustrated. Don't beat yourself up if you're only getting half those points. Totally fine, but please make sure you're checking your work and making corrections and then sending and submitting photos of your work. Before I start, please make sure you have your work in front of you, you have your equation sheet, you have a calculator, and you also have the problems in front of you from that document. Some of you printed them off, which is totally fine. I have them here on my beautiful second monitor. Cool, let's get started. All right, question number 1. Pull that up. You have a rocket. There are 2 parts to this rocket. So that it is accelerating up to a certain point, and it gives us the acceleration as 30 meters per second squared, and it does this for 2 seconds. After that point, the rockets are shut off, and it continues up for some amount of time. It doesn't give you any of that additional information. So we're going to break this up into 2 parts. Here we're say this is part number 1. This is part number 2 here. It starts from the ground here at 0 and it gets to some height up here, which we will solve for in part B. When you're doing these kinematic equations, you need to write out the 5 variables for each of those parts you're analyzing. So we have acceleration, time, velocity initial, velocity final, and distance. Because this is number 1, we'll call this distance 1. We know it starts from 0, so our initial velocity is 0 meters per second. Please do not forget your units. Lots of students were forgetting those last week. Make sure you have those here. In part 2, you also have a distance, which we're going to solve for. Please make sure write them in the same order to keep our work neat. Acceleration, it is in free fall, so it's negative 9.8. The time, velocity initial again, velocity final, and distance 2. How far does it go up? The final velocity at this point for a brief second is going to stop before it changes its direction, and then it will fall back to the ground. So at that very point right there, the final velocity is 0 meters per second. We can fill in also one other thing. This point right here, it accelerates from 0 up until this point. At this point, it has some velocity. Then the rockets are shut off. So the final velocity here is going to be the initial velocity here, which we're going to solve for in part A. So here we go. Part A, determine the speed, so this velocity, after the rockets have been firing for 2 seconds. If you don't draw a picture, go back and draw that right now so that you have that so you can visualize what is happening. So we are trying to find the final velocity. What's it going to be? We have all 3 of our variables, so we can solve for the other 2. However, it didn't ask us for distance, nor did it give it to us, so we don't care about that. We do need velocity final. So I'm going to pick the equation that does not have distance in it, which, because you have your equation sheet in front of you, is equation number 1, which says velocity final is equal to velocity initial plus acceleration times time. Remember on the AP test, you do get some points for writing out your equations. Velocity initial, we know is 0. Velocity final, we're going to start plugging our numbers in, is 30. Time is 2. Velocity final, multiply those together, and you get 60 meters per second. Is that what I was asking for? Yes. Speed after 2 seconds, cool. We can put a box around that. Then I'm going to put it over here, 60 meters per second. The final velocity at this point becomes then the initial velocity for your calculations on this part up here. Totally meant to write 60, not 20. Awesome. That's part A. Part B, it says, what is the maximum height the rocket will reach? So we have this distance and this distance here. So we're going to solve these in two different parts and add them together. So I'm going to write the total distance is equal to the distance it travels while it's accelerating plus the distance that it continues up while it's in free fall. We'll call that distance 1 and distance 2. Distance 1 is right here. I have all four other variables, so I can use any of the equations that have distance in them. I would not want to use equation 1 because it does not have distance in it. So I'm going to go, let's do equation number 2 to solve for distance number 1. On the equation sheet, it says x equals x naught plus velocity initial times time plus 1/2 a t squared. Again, you get points for writing the equations down sometimes. So here we go. This becomes 0. We started off, that rocket starts at 0, so this also is 0. In our equations, we're using distance 1 here, so I'm going to put distance 1 in for the displacement, the distance it moves here. Acceleration, we know. Time, we also know. We have one variable, one unknown. We can solve for that. I'm not going to rewrite it. I'm going to plug this in my calculator or do it in my head. And you get distance 1 is equal to 30 times 4 divided by 2, 60 meters. Should we box this? No, this is not our final distance. This is only the distance it travels here. You have to find this distance as well, so we know distance 1, we need distance 2 as well. I'm going to plug this in over here, 60 meters. Cool. Boom. To solve for distance 2, we have 3 of our variables, but we don't have time, so we're not going to use that same equation. I'm going to pick equation 3. Equation 1 on your equation sheet doesn't have distance in it, so that's not going to help us either. We need distance in order to solve for this. So equation 2 says velocity final squared is equal to velocity initial squared plus 2 times the acceleration times your distance. For us, we're calling this distance 2 to keep our variables in order. Final velocity, it gets to the top, is 0. The initial velocity, remember the initial velocity at this point is the final velocity of this part here, so we know that is 60. Our acceleration when it's in free fall is negative 9.8, distance 2. Cool, we only have one variable, one unknown, so we can solve for this. When you plug it into your calculator, you get 60 squared, pull it to the other side, divide by 2 times negative 9.8. This is multiplied. Remember, this is not 2 minus 9.8. It's multiplying them. Distance 2, you get 13.5. There we go. At what time t0 is the maximum height reached? So we know the maximum height rate here is going to be 73.5. We're going to again break this up into 2 different problems because the acceleration in each of them are different. So we're going to find the time here. Oh wait, we already have it. Now we need to find the time here and add it to the time here. So I'm going to write total time is equal to time 1 plus time 2. We already have this, 2 seconds. Cool, we're good. We only need to solve for this guy right here, which is time. Time 2. We have all the variables except for the time, so we can use any equation that has time in it. My handy dandy hint sheet, I went with equation 1 because it has no square roots. It's the simplest I feel to use without setting yourself up to make mistakes. Least amount of calculator pushing. Final velocity, remember it gets to the top. Initial velocity is 60. The acceleration is negative 9.8, and we're solving for time. Cool. Opposite of this to get over, we're going to subtract it and then divide by negative 9.8. And your time, you get 6 something? Yep. 6.12 seconds. Is this our final time? No. This is only the time for this section here, so we need to add 2 to that. So in this first instance here, it went 2 seconds. This top one here, it is 6.13 seconds. Total time, 8.13 units seconds. Cool. Now you are good to go. Awesome. Pause that there, fix your work, and get ready for number 2. Awesome. Our favorite projectile motion. All right, you have a mass of 300 kilograms. I'm immediately thinking to myself, I love kilograms. I don't need to convert to anything. I have a picture there. I'm going to redraw it over here, like so. It is launched 230 meters above the ground. So here we'll say 0, here up here is 230. This is your Y direction, and then in the X direction, it lands 300 meters away. All right, you need to find the time. Immediately when you have projectile motion problems, you should be dividing this into your X and Y components and thinking to yourself, these are independent of each other, except for time. Time can be in the X and you can be using the X and Y. So I'm going to draw my table here. All my X variables, all my Y variables. In the X direction here, you only have velocity, distance, and time. Why is that? Because there is no external force in the X direction that's making it speed up or slow down. So your velocity here in the X direction is going to be the same as the velocity here in the X direction. It will always be constant. In the Y direction, though, you have acceleration due to gravity, which is 9.8 meters per second squared. Distance, velocity initial, velocity final, and time as well. So time here and time here, these are both the same time. That's what we're going to solve for here. Let's put in a few more numbers that we know. In the Y direction, velocity initial, it is not launched at an angle. It is launched straight out. So that is the same as if you were just to take this pen and drop it down. So your initial velocity in the Y direction is going to be 0 meters per second. Cool. Let's begin. We're going to find time. It doesn't say if you need to find time in the X or Y direction. You could use either. In the X direction, I have 1 known and 2 unknowns, so that will not help me. Here in the Y direction, oh, I have 3 of these, and I need to find time, so I totally can do this. I'm looking at my equation sheet, and I'm going to use the equation that does not have velocity final in it. On that equation sheet, it says x equals x naught. Like so. Cool. Velocity initial in the Y direction is 0. This we're always going to say is 0 as well. In the X direction here, this just means distance, like the distance it falls. We could say here in the Y direction, this is 0, and it falls negative 230 meters down to the ground. 0, down 230. So we're going to say this is negative 230. Don't worry about the negatives and the positives. On this one, they will cancel out. So if you keep this as positive, you're totally fine. But then your acceleration would be positive as well. Cool. 0, 0. So we have 1/2 negative 9.8 times time squared. T time is our only unknown right here. You have your 2 negatives. Like I said, those canceled out. If you accidentally kept this positive and kept your acceleration positive, totally fine. You would have gotten the same answer. So 230 times 2 divided by 9.8, take the square root. So in your calculator, divided by 9.8, you get time is equal to 6.85 seconds. You may box that because you were solving for time. So time here is 6.85 seconds, and time in the Y direction is also 6.85 seconds. Cool. Part A, done. Part B. We need to find the initial horizontal velocity of the projectile. So initial, you're also thinking to yourself, oh, that's a silly question, because the initial is for the horizontal in the x direction is always going to be the same. Kind of a trick question for when you look down then part D as well. Cool, so we have the distance, we have the time, velocity. You can only use this equation if the velocity is constant, which we know it is. So velocity is equal to distance over time, 300 divided by 6.85 is our time. Plug that into your calculator. You get 43.8 meters per second. Cool. I think in the answer key they did a little bit more rounding. Some of these, I think this one's so totally fine if you are doing that and you get, I think they wrote 48 here, or 44. That's fine. All right, part C, moving right along. What is the initial vertical velocity of the projectile? So remember again, it is shot straight out. It only has a horizontal velocity. It does not have an initial vertical velocity. So that initial vertical velocity is 0. Don't have to do any justifying or any math for that. You then need to find the horizontal component of the velocity just before it hits the ground. Oh, that sounds like a lot of angles, a lot of math. Oh, but I'm thinking to myself, the velocity in the horizontal direction, yes, part D, does not change. There is no external force on this x direction. Here you're experiencing the force due to gravity and acceleration due to gravity pulling it down. In the x direction, there is no external force. So there's nothing, the air resistance, there's nothing pushing it or pulling it to make it slow down or speed up. So the velocity is going to always be constant. There's your answer for part D. All right, part E. Find the vertical component of the velocity just before the projectile hits the ground. So we're going to vertical over here. You need to find the final velocity. This is what we are solving for. You can use any of the equations that have final velocity in them. Question number 1, I think, is the easiest. Let's do this. Final velocity, so what we're solving for, initial velocity again is 0. So we have negative 9.8. Oh, time, we already solved for that, cool. Plug those in and you get negative 67.13. The reason why this is negative is because it is the velocity vector is pointing towards the ground. Do not stress if the number is negative. It is totally fine in this case. Cool. Awesome. Part F, it says, what is the magnitude, so what is the number, and the direction of the final velocity? This means the projectile is going to be moving like this, and so we want this hypotenuse here. When we broke it into the x and y components, these are just the vector components. That does not mean that the projectile broke into 2 different pieces. You can just analyze it using the y and x direction. So we need to find what is this hypotenuse here and what is the direction. So they're asking for an angle. So that is that angle here, which is also this same angle here relative to the ground. Here we have x and here we have y. We're trying to find the velocity, so we need the velocity components. In the vertical direction, this is 67.13. In the x direction, you have 43.8 meters per second. This is a right triangle. Maybe you're thinking to yourself, ooh, I love Pythagorean theorem. I'm going to use that. Here is the actual velocity. Let's solve for this first. So we know Pythagorean said velocity squared is equal to one side squared plus the other side squared. So we have 67. Square this, add it to the square of this, take the square root of the whole thing, and you get the final velocity to be roughly 80 meters per second. We're not done yet because we need to find the angle that it is at. So I know here I can use my SOHCAHTOA. This is the angle we're working with. We want to find this angle here. So I see this is opposite, and this is adjacent because it is next to. So if I have A and O, not sine, not cosine, tan. So I know tan of the angle is equal to OA, opposite, divided by, sorry, I thought my computer died, 43.8. But the thing is, we know this fraction, we don't know the angle. So to find the angle in your calculator, you're going to use inverse tan. If you have your calculator like this, it is this button here. You need to write second tan, like so, is what it should look like. And then you put in 67.13. And this is the answer you should have gotten. If you're getting a different answer, a negative answer, make sure your calculator is in degrees, not radians. Remember to do that. You press mode, go down degrees to radians. Awesome. And that is it for part F. What did I say? 56 degrees? Yeah. Degrees. Cool. Now let's talk about this mass here. Part F states, a new projectile, though this original one, remember, is 300 kilograms, is now only a mass of 100 kilograms. How does the final velocity, so what we just found, the 80 meters per second, how does that compare to the original projectile? Briefly explain your answer. I would say mass 1, mass 2 is now 100. Did we use this in our calculations at all? No. Do all things on Earth fall to the Earth, fall at the same rate? Do they experience the same acceleration due to gravity? Yes is your answer. So you would say something like no effect when mass is changed. No effect on what? What does it ask? How does the final velocity? So there is no effect on the final velocity when the mass is changed. Why? This is because all objects cool. Mass doesn't matter. So you could throw a baseball or you could throw a piano out the window. They should all hit the ground at the same time. Awesome. Let's jump to number 3, which is some graphing. Awesome. And this one is way smaller. Here we go. The first 10 meters of 100-meter dash are covered in 2 seconds by a sprinter. It looks like we have to draw some graphing, and then the remaining 90 seconds are the same velocity the sprinter has after 2 seconds. So I know he, let's say, we'll call this part 1. He's accelerating. And then part 2, he is constant velocity. We know this distance here is 10 meters, and then it's a 100-meter race, so the rest of the race is 90. Just wanted to draw a little visual to organize my thoughts on what is happening there. You need to, for part A, determine the constant acceleration during the first 2 seconds. So right here, this is all we care about. What is the acceleration? We know the distance is 10 meters. Initial velocity, he starts from 0. And final velocity and time. Oh yeah, we have time, right? 2 seconds. of acceleration. Sweet. So you're always trying to find 3 variables. If you have 3, then you can start solving for things. Again, we're trying to find the acceleration. We do not have final velocity. So the equation that I'm going to use is equation number 2. Why? Because it doesn't have final velocity in it. 1 and 3 do. So on my equation sheet, it says the distance is equal to initial distance plus initial velocity times time, 1/2 a(t squared). Cool. He starts at 0 position. Initial velocity is 0. We're trying to solve for distance. Call this distance 1. Just kidding. Not solving for distance. This is what happens when you don't drink coffee yet. Acceleration is what we're solving for. Remember, he's moving in a straight line, not moving up or down. And the time is 2 squared. Cool. 1 unknown, 1 variable. Can we solve? Awesome. Yeah. 4 divided by 2. Acceleration, 5 meters per second squared. Remember, this is acceleration, so you have to put in your units of meters per second squared. Cool. All right, part B. Part B, it says determine the velocity after 2 seconds. So that's just asking for your final velocity here. In that 2-second time frame, what is his final velocity? So we have all 4 of the other variables. We can use any equation that has final velocity in it. Number 1, for me, is the easiest. Here it is. Final velocity is what we're solving for. Initial is 0. We know our acceleration now and time. Cool. There we go. Box it as well. Part C. Determine the total time needed to run the full 100 meters. Ooh, nice. Okay, so we know here, part 1, he already took 2 seconds to do this. Here, this part 2, he's moving at a constant velocity and he has 90 meters to go. How long does it take for him to do part 2? And then we're going to add it to part 1. So I'm going to say the total time is equal to time 1 when he's accelerating plus time 2. Here he's moving at constant velocity. So again, we have velocity, distance, and time 2. The distance he goes is 90 meters. The time, we don't know. Do we know his velocity? Yes, we do. We just found it in the last part. So that right here at this point is his final velocity in this accelerating part. So once he gets to that, it tells us in the problem that he just cruises at that same speed for the rest of the race. Cool. Time 1 we have, time 2, remember we're solving for this. So here we can use, again, if you're moving at constant velocity, you can use velocity is equal to distance over time. Distance. So now we have 10 is equal to 90 over t. This time is equal to, you can flip these, time is equal to 9 seconds. Should we box this? No. Why? Because that's just time 2. We need to add it to time 1. So this time plus this time is his total time to run the race, which we have is 2 plus 9. Total time is 11 seconds. Cool. All right, here we go. Part D, graphing. Yes. Okay, on the axis provided, draw the displacement versus time curve for the sprinter. So displacement here, he starts at 0. Here he gets to 10 meters. Here he gets to the whole 100 meters. Remember, this is 90 meters though. From the AP Physics test, if you label, if it says to use appropriate units and whatnot, that just means label the axis, the X and Y, and use over half the graph, and you just get free points there. Cool. It's already given to us though. You have time, and you have displacement. Here he goes up to 100 meters, so halfway is 50. Yours is already drawn. We'll call this 2 seconds. 2, 4, 6, 8. Okay, yours is going to look way prettier than mine. We already know that it takes him 11 seconds to get to 100 meters. So we can already put that dot right there. Cool. He starts at time 0. He's at 0 seconds. We know in the first 10 meters, this is not going to be very pretty, but we'll try. In the first 10 meters, he's accelerating. If he was moving at a constant velocity, we would have a straight line, a sloped straight line, but he's accelerating. So you need to make sure this first part here is curved up into 2 seconds. Remember, this is displacement time. Can you see that's a beautiful curve? And then for the rest of his race, he runs at a constant velocity. On the displacement time graph, so rise over run, distance over time, gives us velocity. So the slope of this graph then is going to be the velocity. If the velocity here is constant for the rest of the race, we need to show that that is a perfectly straight line. So because you are all way better drawers, no, dang it. Should have just lined it up. Here we go. There we go. So here this is constant, here this is sloped up. Beautiful graphic. Awesome. Cool. Let's jump to number 4. Been going 32 minutes. We're going to finish the next 10 minutes. Cool. FRQ number 4. Again, we have a graph, but this time we have a car and a motorcycle. At t = 0, the car and the motorcycle are shown in the same location. Be very careful. This time the graph is velocity time. Velocity time. Be very careful of that. In a paragraph length response, without using equations, explain the motion. So they just want to know what the car and the motorcycle are doing. Key points. The car. On the answer key, they have a great paragraph length example. See what I see. Oh, that's good spelling. I'm going to do some bullet points on what you should have there. So I see the velocity of the car is constant. How do I know this? Because the velocity time graph, like this, the velocity, let's say it starts off at 20, it's going to add 5 seconds, it's going to be 20, because this is time down here, it's going to be constant the whole time. Awesome. We have a motorcycle that goes like this, though. It is not constant. So the velocity here starts at 0. The velocity, remember here, let's say at 15 seconds is 10. And it keeps going up and up. So the motorcycle starts at 0 and he is increasing his speed. If you're changing your velocity and increasing it, we're going to say he has a positive acceleration. Awesome. This one, the car, constant velocity, so we could say it's not accelerating. This one, positive acceleration, you can say the velocity is changing. Starting at 0. Cool. Oh, we need to add something. It says to add position. They're both moving in a positive direction. The reason I know that is because, remember, a velocity time graph, the area under the curve, so this is a curve, this is our curve, is your displacement. If this area is positive, that means that it has a positive displacement. If these lines were under the curve, then it would have a negative displacement. That just means it would be moving in the opposite direction compared to your observer. So here we go. These are the points for part A. All right, part B. Besides time equals 0, you need to determine the time at which the car and the motorcycle are at the same spot and justify your answers. Same spot. So that means their displacement are equal. Excuse me. I know velocity time graph. The displacement is the area under this curve. So this is for the car. Didn't plan to do this, but we'll see how it works. And here, this is the area for the motorcycle. So when their displacements, the area under these curves are the same. You could look at this graph and be like, oh, well, doing a little guess and check, I see at time is equal to 60 seconds down here. The car is equal to, it's a rectangle, so we have the height here is 20, times the base is 60, don't need to do any conversions, is 120 meters. What about the motorcycle? Cool. So the motorcycle at 60 seconds, it is a triangle. So there's a blue area here. Area for a triangle is 1/2 base times height. Can we see that? We'll just go back to black. The base is 60 again, and the height, though, it gets all the way up to here, which is 40. So we have 60 times 40 times 1/2. Again, you get 120 meters. Awesome. So they've both gone 120 meters. So the part B says the time when they've both gone 20 meters, which is at 60 seconds here. We did this by finding the area under the curve for both of them. All right, part C. It says derive an expression for the position of the car and the motorcycle as a function of time. Do not panic with this one. We leave that too. Okay, so you need an expression. That means you need an equation. So something equals something else. What do you need in it for the position of the car? We'll put position because that's what it says. And then we'll change it from what we've been using as position, distance. As a function of time. So we need something with time in it. So if you're looking at your equation sheet, do we have any equations that have position and time in them? Equation number 2 says the position is equal to the initial position plus the initial velocity times time plus 1/2 a t squared. Position, x, these are interchangeable, so we're good to go with these. What about time? Is this some function of time over here? Yes, is your answer. So we're going to build off of this equation here. Let's do the car first. The car is moving at a constant velocity. So I'm going to say x, the position, is equal to the initial position. It starts off at 0. Cool. The initial velocity is 20 times time. We want this in our equation. Plus 1/2 a t squared. Remember from part A when we were talking about the acceleration of the car is the velocity is 20 the whole time. So the acceleration is actually 0. So we can get rid of this whole term. So now we have x is equal to 20 t. That's all you got to do. Now let's do the motorcycle. All right, using the same equation, cool. X is equal to x initial, starts at 0, plus velocity initial times time, plus 1/2 a t squared. Cool. X is our position, it starts at 0 again. Initial velocity of the motorcycle is 0. So our equation becomes 1/2 a t squared. It doesn't say with a function or as with acceleration. So we need to find some term for acceleration to make this just a function of time. When it says function of time, that means that will be your only variable. If I see on my velocity time graph, I know something. I know the acceleration from this graph. It is not the area. The area is the displacement, but our slope here is actually our acceleration. Because you're looking at a much bigger, better picture in your computer and not this one that I drew here, you can use that graph to find the acceleration. So we want the slope of a VT graph is the acceleration. Cool. We can totally find that from here. You find your slope to be 2/3. So that's rise over run. Remember, slope is rise over run. I need to verify my numbers that were correct on here. So the rise here, you can pick any point on your line. Rise over run. So we're saying it went 10 over 15, which is 2/3. And your function of time becomes like so. Cool. We can even label these as car and motorcycle. Awesome. Cool. Well, that is it for today. No! Did that stop recording? I don't know. Okay, that is it for today. I will see you guys in office hours. Please remember to submit your work and your corrections based either on the answer key or this video that you watched. And don't hesitate to reach out if you have any questions. See you next week.